So we can now look at buffers and how they work now that we've considered how weak acids and weak bases. So how do buffers work, first of all? Well, a buffer it requires a weak acid, first of all. So if we look at the equilibrium for weak acid, we know that from Le Chatelier's principle, if we add more acid or protons to this equilibrium, it will obviously shift towards the left. And that's because it needs to remove the added H plus ions. And the idea is that Ka is restored to its original values. So Ka for ethanoic acid is very small, 1.74 times 10 to the minus 5. So that means that the equilibrium is mainly towards the left hand side. So if we say the concentration of our ethanoic acid is 0.1 mole per decimeter cubed, and we substitute Ka in and work out the concentration of H plus ions, we can see that we only actually have a concentration of 1.32 times 10 to the minus 3 moles per decimeter cubed of H plus ions, which is really very small. And if we now look at how many moles we would have in 100 centimeters cubed of solution, we would only have 1.32 times 10 to the minus 4. And again, that compares to a concentration or a number of moles of 0.0999 of ethanoic acid. So we'd only require a very small amount of added acid to react with all our ethanoate ions that we have there, and our system would no longer be in equilibrium. So let's look at how we make a buffer up and what it is. Well, a buffer solution is one which will minimize any change in pH on addition of a small amount of acid or a base. So an acidic buffer will obviously have an acidic pH and is made up of a weak acid and the salt of a weak acid. So the weak acid provides us with lots of the acid molecules, so lots of ethanoic acid molecules, and adding sodium ethanoate means that we also have in the equilibrium lots of ethanoate ions. So we have our ethanoic acid, which is in equilibrium, and we also have our sodium ethanoate dissolving in water, which obviously isn't in equilibrium, but will contribute ethanoate ions to the equilibrium. Basic buffers, very similar, but made from a weak alkali now and one of its salts. So a typical one is ammonia. If we dissolve ammonia in water, most of that equilibrium is to the left-hand side, and therefore if I add in some ammonium chloride, for example, that will give me lots of the ammonium ions as well. So let's have a look at how an acidic buffer actually controls the pH. So this is a general weak acid, HA, and so we can write Ka for that equilibrium, and we can rearrange that equation to give us our concentration of H+. And so if we go back to that, our pH of the acidic buffer purely depends on the ratio of HA to A-, because Ka, of course, is a fixed value at a certain temperature. So if we now add some acid to an acidic buffer, then our concentration of H+ will increase. The ethanoate ion will react with that acid to neutralize it, and the equilibrium will move to the left. And of course we have lots of ethanoate ions from the sodium ethanoate that we've added. So we can now look at the effects of adding alkali to our acidic buffer. Obviously our concentration of OH- will increase. Our H+ ions will react with that added hydroxide to produce water, which neutralizes those additional OH-, and our equilibrium will move to the left. This causes our ethanoic acid to dissociate, and that equilibrium will shift to the right to restore the H+ ions, and hence the pH of the buffer. So let's look now at how an alkaline buffer solution controls pH. So we'll take ammonia as an example. Ammonia, of course, is a weak base. and produces the ammonium ions in solution along with hydroxide ions, but that equilibrium is towards the left-hand side. So we can write Kb for this equilibrium because obviously we're looking at bases now rather than acids. And of course the ammonium ions have been added in using a salt like ammonium chloride. We can rearrange this to now give us the concentration of hydroxide ions, and we can see that the pH, which is of course related to the concentration of hydroxide ions, will be dependent on the ratio of the base to the salt. So we can now look at the effect of adding alkali to our buffer. So if we add OH minus ions, then they will be removed by reaction with the ammonium ions to form NH3, and the equilibrium will shift to the left-hand side. So that means our concentration of ammonia will rise slightly, and the concentration of ammonium ions will fall slightly. But as the concentrations of both ammonia and ammonium are much greater than hydroxide, that ratio remains fairly constant, and that means that the pH will stay constant as well. So in the next video, we will look at putting some numbers into those equations to do some calculations.